Have you ever tried to put two parts together, maybe while fixing something at home or working on a project in the garage, and found that no matter how hard you tried, they just didn't fit? It's a common frustration, but it's also a fundamental challenge in engineering and manufacturing. This is what we call a problem of fit, a core concept that underpins how machines and devices are built and function. Fit isn't just about whether something is too big or too small, it's about the precise relationship between two parts, how they come together, interact, and move relative to each other. This relationship, known as a mechanical fit, is what makes everything from car engines to door hinges work smoothly and reliably. Without the right fit, machines can jam, wear out quickly, or even fail completely. A fit is the planned difference in size between two mating parts, like a shaft and a hole. This difference is carefully designed to achieve a specific function. Sometimes you want the shaft to spin freely inside the hole, like in a wheel bearing. Other times you want it locked in tight so it doesn't move at all. That's a crucial design choice that affects performance and durability. To control this, engineers use tolerances, acceptable limits of variation in the size of each part. Tolerances ensure that even with tiny differences in manufacturing, the parts will still work together as intended. The two main players in this story are the hole, which is any internal feature, and the shaft, which is any external feature that fits into the hole. The difference in their diameters determines how they interact, whether the shaft slides in easily, needs to be pressed in, or requires a hammer to force it together. Each scenario serves a different purpose in mechanical design. Mastering fits allows engineers and builders to create assemblies with incredible precision, whether they want smooth, effortless motion or a permanent, unbreakable bond between parts. There are three main types of fits: interference, clearance, and transition fits. Each type has its own unique characteristics and applications. Let's break them down and see how they shape the world of engineering. First up, let's talk about the interference fit, sometimes called a press fit or force fit. This is a classic technique in mechanical engineering, and it's all about using the power of tight tolerances to create incredibly strong connections between parts. In an interference fit, the shaft is actually made slightly larger than the hole it needs to go into. This isn't a mistake, it's done on purpose to create a super tight fit. To assemble these parts, you need a lot of force, sometimes using a hydraulic press or even heating one part to expand it before assembly. These temperature tricks make the process easier and ensure a perfect fit. Once the parts are joined, they're locked together so tightly that they act as a single solid unit. There's no play or movement between them at all. You'll see interference fits used when you want absolutely zero movement, like when a gear is pressed onto a motor shaft, ensuring it spins perfectly in sync. Or think about a bearing inside a skateboard wheel, pressed in so tightly that it won't budge, no matter how hard you ride. The secret here is friction. The immense friction between the tightly fitted surfaces holds everything firmly in place, resisting any forces that try to pull them apart. But there's a catch. Interference fits demand extremely precise machining. If the fit is too tight, you risk breaking the parts during assembly. If it's too loose, the connection can slip and fail. That's why interference fits are chosen for permanent high-strength connections where you don't want to use bolts, screws, or other fasteners. It's engineering's version of brute force, but done with incredible precision and elegance, creating robust, reliable connections that last. Now, the opposite, clearance fits. The shaft is always smaller than the hole, leaving a gap for movement. This is the fit of freedom. Think door hinges or spinning wheels. The gap allows parts to slide or rotate smoothly, often with a bit of lubricant. Pistons in engine cylinders use clearance fits to move rapidly without seizing. The right amount of clearance prevents binding but avoids sloppiness. Designers pick the clearance based on speed, load, and precision needed. Clearance fits are everywhere. Whenever you want parts to move, it's all about just enough space to do the job right. Between the extremes is the transition fit. Here, the shaft and hole are so close in size that you might get a tiny gap or a slight interference, depending on the parts. Sometimes they slide together, sometimes they need a gentle tap. Transition fits are for precise alignment without the permanence of a press fit. Think dowel pins aligning machine parts, snug but still serviceable. They hold parts accurately, resist vibration, but can be disassembled if needed. Used for couplings, gears, or flanges that need exact location but not a permanent bond. Transition fits are the perfect compromise, precise but practical. Let's sum it up with a clothing analogy. Imagine your wardrobe as a toolbox of fits, each serving a unique purpose. Clearance fit, like a loose jacket, easy movement, no restriction. It's all about comfort and flexibility, allowing you to move freely without any constraints. Transition fit, a tailored suit, snug, precise, but not tight. It's the perfect balance, offering a sleek look while maintaining comfort. Interference fit jeans, 2 sizes too small, hard to put on, not coming off. It's a struggle, but sometimes necessary for a secure hold. Clearance shaft, smaller than hole, parts move freely, door hinge, wheel. This fit is ideal for parts that need to rotate or slide effortlessly. Interference shaft, larger than hole, parts locked together, bearing gear. This ensures a firm grip, preventing any unwanted movement. Transition sizes nearly match, snug fit, dowel pins, couplings. It's about precision, ensuring parts align perfectly without being too tight. Understanding these fits is key to good design. It's the foundation of creating functional and efficient systems. It's the difference between assembling parts and engineering a solution. A well-thought-out fit can transform a simple assembly into a masterpiece. Don't be intimidated. Just ask, do the parts need to move or stay put? This simple question can guide your design choices. Choose the fit that matches your goal. Whether it's flexibility, precision, or security, there's a fit for every need. Now you're ready to build with confidence. With the right fit, your projects will not only function well, but also stand the test of time.